Hello, welcome to my video series of data structures. This is part 3 of Module 8, the graph data structure. In this video, we will discuss the topological sort algorithm for directed acyclic graphs. As the name suggests, a directed acyclic graph, also known as DAG, is a directed graph that does not contain any cycles. Recall that a cycle occurs when there is a path in the graph that starts and ends at the same node. For example, consider the graph shown here. If we follow the path A to B to C to A, we see that it starts and ends at node A. Since this forms a cycle, we say that the graph contains a cycle. A DAG is a special type of graph that effectively represents feasible dependency networks. In this representation, each node corresponds to a task, and each edge indicates the precedence dependency between two tasks. For example, if task A must be completed before task B, we draw a directed edge from A to B. The resulting graph is directed, with edge direction signifying task precedence. To ensure that all tasks can be completed, the graph must also be acyclic. Otherwise, deadlocks may occur. For example, consider the directed graph shown here. It contains 3 tasks to complete: slay the dragon, level up, and acquire the sacred sword. The dependencies indicate that you must acquire the sacred sword before slaying the dragon. You must slay the dragon so that you can level up. And you must level up to have enough power to acquire the sacred sword. This forms a cycle, creating a deadlock where no task can be completed. To avoid such situations, dependency graphs must be acyclic, ensuring that tasks can be completed in a valid order. Thus, a DAG serves as a reliable structure for representing feasible dependency networks, guaranteeing that all tasks can be successfully finished. Another example of a DAG is a curriculum map. In a curriculum map, each node represents a course required by the degree program, and an edge indicates a prerequisite relationship. That is, the source course must be completed before taking the target course. A curriculum map must be a DAG. Otherwise, a cycle would form, making it impossible to complete the degree program. Given a DAG, we need to develop a schedule that allows us to complete all tasks while respecting the precedence dependencies indicated by the edges. For example, when planning a course schedule, we must ensure that all prerequisite requirements are met before taking dependent courses. This type of ordering is called a topological sort of a DAG. Formally, a topological sort is an ordering of nodes in a DAG, such that if there is a path from Vi to Vj, then Vj appears after Vi in the ordering. Intuitively, we should start with a task that has no prerequisites. In the corresponding DAG, A task with no prerequisites is a node with an in degree of 0, meaning that it has no incoming edges. But does every DAG always contain a node with no incoming edges? Let's explore this question by considering the following proposition. Proposition 1. In a DAG, there is always at least one node with no incoming edges. We will prove this by contradiction. Suppose, for the sake of contradiction, that every node in a DAG has at least one incoming edge. Now, let's pick any node and begin traversing the graph by following its incoming edges backward. For example, say we start at node Vi. In the next step, we follow an incoming edge of Vi backward to visit Vi-1. Again, we follow an incoming edge of Vi-1 backward to visit Vi-2, and so on. Since we assume that every node in the DAG has at least one incoming edge, we can continue this backward traversal indefinitely. Let the DAG contain V distinct nodes. After V steps, we have visited V+1 nodes. Since the DAG contains only V distinct nodes, but we have visited V+1 nodes, we must have visited at least one node twice. By definition, revisiting a node implies the presence of a cycle. This contradicts with the fact that the graph is acyclic. Thus, our assumption must be false, proving that every DAG must contain at least one node with no incoming edges. Now that we know every DAG must contain at least one node with no incoming edges, we can use this node as our starting point. This selection is valid because the node has no prerequisites, meaning it can be completed first. Once we complete the first task, we remove its corresponding node from the DAG and move on to the next task. Ideally, the next task should also have no incoming edges, meaning that it either has no prerequisites or all its prerequisites have already been completed and removed from the graph. However, can we be sure that such nodes will always occur after removing the first node? We will address this question using Proposition 2. Proposition 2. Removing a node from a DAG results in another DAG. To prove this, first know that removing a node does not change the direction of any existing edges. Since we are only deleting a node and its associated edges, the graph remains directed. Second, removing a node does not add any new edges to the graph. Since new edges are not introduced, no new cycles can be created. Because the resulting graph is still directed and acyclic, removing a node from a DAG always results in another DAG. Using propositions 1 and 2, we can construct the following algorithm to generate a topological sort of a DAG. We begin with the given DAG. By proposition 1, there exists at least one node, U, with no incoming edges. We perform the task corresponding to U, then remove it from the DAG. Since U has no incoming edges, completing it satisfies all precedence dependencies. By proposition 2, removing U results in another DAG with one fewer node. Since the new graph remains a DAG, proposition 1 guarantees that there exists at least one more node, U prime, with no incoming edges. And we can repeat the same process for U prime. Perform the task, remove U prime, and continue. This continues until the DAG becomes empty, meaning all tasks have been completed in a valid order. In the above process, we only perform a task when its corresponding node has no incoming edges. This ensures that the task has no prerequisites, or all of its prerequisites have already been completed and their corresponding nodes have been removed from the graph. Since every task is executed only when it becomes valid, the topological sort algorithm is correct. Know that a DAG may contain multiple nodes with no incoming edges at any step. Since our algorithm does not specify which node to choose first, different choices can lead to different valid topological orderings. Therefore, a given DAG may have multiple valid topological sorts. Here is the pseudocode for the topological sort algorithm. In line 2, we use a while loop to iteratively schedule a task and remove its corresponding node from the DAG. Since we process one node per iteration, the while loop runs OV iterations. In line 3, we identify a node U with no incoming edges. This requires OV time, as we need to examine each node. In line 6, we remove U and all its associated edges from the graph. When using a adjacency matrix, node removal takes OV time. When using a adjacency list, node removal takes OD time, where D is the average node degree of the DAG. The bottleneck of the algorithm is the OV time spent per iteration to identify a node with no incoming degrees. Since there are OV iterations, the total time complexity is OV squared, regardless of the specific implementation. To mitigate the bottleneck of repeatedly identifying nodes with no incoming degrees, we use a queue Q to store such nodes. When removing a node, no edges are added to the graph. Therefore, nodes already in queue will not gain new incoming edges and should remain in queue. However, removing edges associated with a deleted node reduces the in degree of its neighbors. If any neighbors in degree becomes 0, it should be added to queue. For example, consider the graph shown on the left. When deleting the blue node U, we also remove its associated edges, including the two outgoing edges indicated by broken arrows. This affects the yellow nodes V and W. After removing U's edges, V has no incoming edges and should be added to Q. On the other hand, W still has one incoming edge and should not be added to Q. This idea is implemented as the delete and recruit function shown on the right. Here, we assume the adjacency list implementation. The function takes three input parameters: the graph G, the node to delete U, and the queue that stores all nodes with no incoming edges. In line 2, it updates the node array V to remove U. In line 4, it uses a while loop to traverse LU, the linked list storing U's outgoing edges. In line 5, it reduces the in degree of each target node. In line 6, it adds a target node to queue if its in degree becomes 0. Since all steps inside the while loop run in O1 time, and we traverse D outgoing edges, the overall time complexity is OD, where D is the degree of U. Here is the updated topological sort algorithm. In lines 2 and 3, we initialize Q with all nodes that have no incoming edges. Then, we iteratively process tasks using the while loop in line 4 until the graph becomes empty. In lines 5 and 6, we extract a node U from Q and perform the corresponding task. In line 7, we use the delete and recruit function to remove U from the graph and add newly eligible nodes whose in degrees become 0, if any, into Q. In this version, each iteration within the while loop can be completed in O1 plus D time. Since the while loop runs OV iterations, the time complexity becomes OV plus V times D. The time complexity further simplifies to OV plus E, as the number of edges E can be estimated by the product of the number of nodes V and the average node degree D. When the DAG is sparse, the time complexity evaluates to OV, which is more efficient than the original version of the algorithm. In this video, we introduced the topological sort algorithm for DAGs. A DAG is a directed graph with no cycles, commonly used to represent task dependencies and precedence constraints. A topological sort of a DAG provides an ordering of nodes that ensures all tasks can be completed while respecting dependency rules. To derive the topological sort algorithm, we proved two important propositions. First, every DAG contains at least one node with no incoming edges. Second, removing a node from a DAG results in another DAG. Using these propositions, we developed an algorithm that iteratively outputs a node with no incoming edges and removes it from the graph. Since each output node has no remaining dependencies, the algorithm guarantees correctness. With proper optimization, the algorithm achieves OV plus E runtime. Thank you for watching, and see you next time.